So our topic today is diagnosing vehicle communication issues. So those can be prevalent and those can be kind of a pain to diagnose. U codes can help a little bit to an extent, but sometimes they're not much help at all. So really we have to go through the wiring diagrams and understand kind of how the network works and how networks in general work inside the vehicle in order to be able to test them. So that's kind of what we're going to cover here. A little high level overview of different networks, and then we'll dive into some wiring diagrams and take a look at how a couple different vehicles are laid out. So let's define a network. Networks are a system that utilizes information through all available resources. So any resources that are connected. So in the vehicle sense, let's say RPM is sent out by the ECM and the TCM needs it, and maybe the analog brakes needs it for some reason. Vehicle speed comes out of the transmission perhaps, and then uh, traction control would need that, or whatever the combination is. But they feed information to all the other modules that might need it on the network. So different types of networks you may already be aware of. So LAN is a local area network. So that is, think about that as the Wi-Fi in your shop or at your house. That's your local network. All the connected devices are connected to it. WAN is wide area network. So that's multiple different LANs connected together over a wide area. That's just kind of a complicated way of describing the internet. Then the types of networks that we'll be dealing with in the automotive industry, at least a couple of the newer ones, I guess. CAN, which is controller area network, not car area network like some folks might think. Controller area network is not only used on vehicles, it's also used in factories for automation and other things. So it's just for different controllers networked together. LIN stands for local interconnect network. So you might hear LIN bus thrown around out there. So that we'll talk a little bit more about that. And then DOIP, which is the newer one, it's Diagnostics over IP, which works pretty much like your network would work at your shop or your house. So any network is going to work on what we call a voltage differential, the difference between the high side and the low side of this pattern we have here. So mainly they're going to be in a square wave type pattern. So in this case, we're looking at a LIN bus, and LIN transmits the little ones and zeros, the bits and bytes, all the networks. That's all computers know is 1 and 0, on and off, binary code, right? So anytime we see a pulse up, that's on, pulse down is off, or vice versa, depending on how the manufacturer has it set up. But just know that each of these pulses represents a 1 and a 0. So this works on a 12-volt differential. Now you see it's a little over about 13.35 volts. And then it comes down to 0.91 volts, so it does not go down all the way to 0, and that gives us a roughly 12-volt differential right there, so 12.44. So anything in that threshold is going to be considered valid. So if I needed a 12-volt threshold and I had this 12-volt above 12 volts, then we're good. If I had a 12-volt threshold and I was getting 10 volts on a pulse, then the computer might not even recognize that as valid data. It'd be weak data. It wouldn't be crossing that threshold to be valid as a 1. So it depends on the computer system once again. But if you have a weak signal, that might be your communication problem right there. And we'll take a look at a couple examples a little bit later. So different communication networks that we're going to deal with in the automotive world is going to be low-speed networks like our J1850 variable pulse width, which GM used to use in the past. J1850 pulse width modulated, which Ford used in the past. K-line, which a lot of Asian vehicles use. Local interconnect network, the LIN we talked about earlier. CANFD, which is a newer version of CAN. We'll talk about that. Flexray, which is kind of like CAN, but a lot faster. Then we have MOST, which is media-oriented systems transport. So that is for media, like CD players and radios and amplifiers and things like that. And then Ethernet, which is that DOIP. So that is actually using Ethernet in a vehicle, just like you might have in the walls of your house or in the walls of your shop. So it's the same type of protocol, and it's much faster and much more efficient for transporting all the data that we have in cars nowadays. Now, one of the more convenient places to test your networks are going to be your data link connector, right? So it's right there. It's under the dash, easy enough to get to. And there are some standardized places where these networks need to terminate. So pin 1 is often used for low-speed CAN communication, single-wire CAN. Pin 2 is J1850 variable pulse width or J1850 pulse width modulated positive side. and then negative sides on pin 10. Pin 4 and 5 are always ground. Pin 16 is always power. So you know if you don't have power at the pin 16, you know you might have a problem with the fuse or somewhere in the wiring, somewhere like that. Pin 6 and 14 is going to be your CAN bus, your main CAN bus. There can be other multiple medium speed CAN and low speed CAN and other CAN bus communication pins on other pins. But the main engine transmission body, all that will be on pin 6 and 14. And then pin 7 is K line for keyword. And then pin 15 is L line if they have one to match. Some manufacturers do both. Some manufacturers just do the K line. So you would be able to test it here. And you see there's a fair number of free terminals, like 3 and 11. 3 and 11 would be another common one that gets used in there. Some manufacturers fill up the whole thing with network terminations. So our low-speed single wire and low-speed dual wire networks here. J1850 variable pulse width consists of a single wire, transmission rate of 10 roughly kilobits per second. It uses a 7-volt differential. So if I was going to look at this on my scope, I would see 7 volts from point to point. J1850 pulse width modulated bus consists of a 2-wire bus with a much faster data rate of 41.6 kilobits per second, and it uses a 5-volt differential. So we see here is about 7 volts right there at the top of the square wave. So that's your J1850 variable pulse width. And then you have J1850 pulse width modulated over here as well. So you can see how they kind of mirror each other. We got a high side and a low side. And then the pulses are a little bit wider, a little bit narrower. So the both sides kind of tend to mirror each other in this case. And you see some are higher, some are lower with that one. That's kind of a unique pattern out of all these. Then we have K-line. So that consists of a single wire with a transmission rate of 10.65 kilobits per second. K-line uses a 10-volt differential. So if you see here, we got 10-volt square wave, right? So going across the screen, lots of ones, 0, 1, 1. See all the different communication patterns. And then LIN bus. So LIN was specially stands for Local Interconnect Network, by the way. Was specially developed to achieve cost-effective communication for intelligent sensors and actuators in motor vehicles. It's a master and slave type situation. So think of things like to save complexity on the window motor circuit. I press down on the window switch. It's going to send a signal. That'd be the master. It's going to send the signal down to the window motor, and it's going to tell the window motor roll down or roll up or express down or express up or whatever it happens to be. So instead of having to go do different control modules and ground relays and stuff like that, it just sends the information over this network, the single wire network. Used wherever the bandwidth and versatility of CAN are not needed. It's kind of a dumb system. If you think about it, it's just kind of off or on, open, close, that sort of thing. LIN bus consists of a single wire with a transmission rate of up to 20 kilobits per second, and it uses a 12-volt differential. So things like roof, sunroof, any of the switches on your steering wheel are more than likely going to be LIN bus nowadays. Seat motors and switches, sensors and small motors on the engine even, grill shutters, things like that. Things that are small, mirrors, mirror switches, window lifts, seat controls, door locks, door motors, that sort of thing. Window lift. All right, and then we saw this earlier, right? So it's a 12-volt differential. It's going to be a square wave pretty much. How wide the pulse is going to be multiple ones in a row or just a single one in a row or and so on and so forth. And the computer can interpret that as whatever the data is trying to say. And then we get the CAN. CAN is probably the most widespread network topology or topography or network communication protocol. There we go. That's what I'm looking for. Probably the most common network communication protocol around now. It's been around for quite some time. So there's different speeds. There's low speed, high speed, mid speed. High speed CAN consists of 2 twisted wires with a transmission rate of 100 to 500 kilobits per second. And it uses a between 2 and 2.5 volt differential. There's a little bit of a range that's allowed in the spec. One signal circuit is identified as CAN high and the other one is CAN low. At each end of the data bus, there's also a 120 ohm termination resistor between CAN high and CAN low circuits, and that's kind of your stop sign. That's the end of the line. Usually, that 120 ohm termination resistor is going to be inside a control module. Right? Could just be sitting out in the open, but more often than not, it's going to be sitting inside a control module. And if I'm going to use a multimeter to check the resistance across pin 6 and 14, I should get 60 ohms roughly, because we're doing 120 ohms on each, and we see it, and then it divides by 2. And that's how we get our number. So a simplified CAN bus here. We got high side, low side, and then we have the termination resistors across both. Nice thing about CAN is it's modular, so I can add multiple modules to it, and they'll start talking. I can add even more modules to it if I want, and they'll keep talking. However, in recent years, I don't know, not that recent, I guess it's been probably the better part of a decade, manufacturers had realized that, hey, now that we have so many modules on these buses, we're having data collisions, and data's not making it to where it needs to in time, and traffic jams and all that. So they decided to move out and branch off into other multiple buses in a couple different ways they could do it. They could either terminate the buses at the OBD2 port, or they can have it go through a gateway module, which would separate it out. And we'll talk about gateway modules here in a little bit. Or other ways that we might see a little bit later with like breakout blocks and stuff like that, or termination blocks. And also, we can remove all the modules but one, and then one module will talk. Because guess what happens when you hook a scan tool up to a network? It becomes another module on that network. So in order to communicate and use those protocols, it has to act like, hey, I'm one of you guys, right? Come talk to me. Give me your data. So even one controller on a CAN bus will work. And here's kind of what it would look like on a scope. So you see we have our data packets in here. We have our idle state, and we have our transmission state. You see how they go kind of on either side of the center line there, that idle line there. If I was shorted to ground, I'd see stuff going on down here. If I was shorted to 5 volts, I'd see stuff going on here. 12 volts would be off the screen. And once again, 6 and 14, but double check your wiring diagrams to be sure that the network you're testing, or the module that you're testing, is on the network wiring that you're testing. Because like I said, they could terminate multiple networks here. Now let's talk about CANFD. So CANFD is kind of the newer version of CAN that's out there. Some manufacturers use it. Many manufacturers use it internally on the vehicle. It doesn't terminate out to the DLC. Sometimes it does, but most of the time it doesn't. CANFD stands for Controller Area Network Flexible Data Rate. So it's CAN bus just with extra stuff. Structurally, it's identical. You can use CAN modules and CANFD modules on the same network interchangeably. It doesn't really care, make a difference. Twisted pair wires, once again, 120 ohm termination resistors. Due to the data structure, however, they can carry more data and faster, anywhere from 3 to 8 times faster than that of traditional CAN. So nerd stuff. If we see how the data is laid out in traditional CAN, you can see just kind of how it's set up there. I'm not really going to describe any of this stuff because that's getting way too deep in the weeds. But you see down here, that matches that, that matches that. We have this new bit here that goes there, and then we have some other stuff in here, and that allows it to compact and expand the amount of data that it's able to carry just by kind of reconfiguring how the data is set up. So don't need to get all the way into that. I'm not an electronics engineer by any means. I know just enough to be dangerous, I guess. As an example on a 2023 Mach-E. So as you see from the diagnostic connector, it's diagnostic CAN. So it's still regular CAN. But then I see up here, I have high-speed CANFD, and I have high-speed CANFD right there. So it has CANFD internally inside the vehicle through the gateway module. Then we have Flexray. Flexray is used on a lot of European vehicles. I know BMW for sure uses it a lot. Mercedes uses it a fair amount as well. It is similar to CAN, but it's not CAN. Consists of 2 twisted wires, similar to CAN, with a transmission rate of up to 10 megabits per second, so considerably faster than CAN. Flexray uses a 1 volt differential. We're getting down in voltage differences because of the speed of how quickly they have to switch on and off from 1 to 0. So it doesn't have a lot of time to move up and down. One signal circuit is identified as signal high, and the other one is signal low. At each of the end of the data bus, there's an 80 to 100 ohm termination resistor between the high and low circuits. That can vary. There's a range allowed in the spec. And then there's kind of what it would look like. So we see lots of ons and offs and ones and zeros, but you see it's very, very small, very small. Now, for data to be sent between networks in a vehicle, like high-speed CAN and low-speed CAN, or CAN to LIN, or whatever it might need to be, a gateway module must be used to translate the signals between them. Another way to think about that is like they are a router on the vehicle's network. So if you think about your Wi-Fi router or regular router at your shop or your home, it directs the signals where they need to go. So this does the same thing. This is not to be confused with the secure gateway modules that they've had over the last few years that like Chrysler came out with in 2018. Some manufacturers do, though, use like pull double duty with it, right? So they know they need a gateway module anyways to translate the signal, so they just make that the first stop from the DLC and then make it secured. So it kind of just does both. Now, in this case, this is I think it was an Impala that we were working on. And they were having a communication issue with the vehicle. They couldn't communicate with anything on the high-speed bus. They were, however, able to test other modules with the scan tool, and it was everything on the low-speed bus was able to be communicated with. So it did a little bit of digging. Come to find out, on this car, you see that there's the DLC right there. First stop after the DLC is going to be the body control module. And on this particular vehicle, that body control module is the gateway module for this car. So it wasn't translating and allowing out the high-speed information. It was only allowing out the low-speed information. So replace the module, set it up, everything worked as it should. So sometimes communication is not even in the bus itself. It could be in a module itself, such as this body control module. So let's talk about testing. In order to test networks, you need to use a lab scope in order to test and see these signals like I've been showing you on the screen here. Using a lab scope feature, we can use our Snap-on scan tool. We can really use anything with a scope, but of course, I'm showing Snap-on equipment, so I'd be talking about Snap-on equipment. But access the pins at the DLC connector for the network you're working on. So like I said, refer to a wiring diagram when in doubt and make sure you're putting it on the right pins. It's recommended to use a breakout box to lessen pin damage. You don't want a front probe, and it's usually hard to back probe, so we're just going to use I'll show you a breakout box in a second. Set the voltage scale to 10 volts to start. This is for CAN, but any of them, they're pretty much would be in that range, except for the ones that are like 12 volts. Then you put it in a 20-volt range, I guess. Set the sweep time at 100 microseconds, and we'll see what we get. Here's one example of breakout box. There's many different breakout boxes out there by many different manufacturers. This is our Blue Point one, the YA11167. So that plugs into the DLC. It's got a short cable. It's got a DLC on the other side to plug in your scan tool. And then this is 16 pins to match the 16 pins on the DLC. And then you would just tap in there, whatever signal you wanted to read into your scope. And it's going to look something like this. Kind of. It's the best we could do with PowerPoint animation. But you'll see stuff going back and forth. You'll see the data going back and forth. So we have a high range and a low range. So the high range is about 3.75 volts on the high side, and then 1.25 volts on the low side. And then in between, when the bus is idle and not communicating anything, that is 2.5 volts should be on both lines. When it transmits, it's going to go up by about a volt, volt and a quarter, down by about a volt, volt and a quarter. And they should match on either side. I'll show you some examples of where they wouldn't match or where they don't match, and there's a problem. Ones and zeros, ones and zeros. All right, so like I said, we're only interested in these following thresholds: the 3.75 volts on the high side, 1.25 volts on the low side, 2.5 volts in the middle, and everything needs to stay within that range. If I have electromagnetic interference, like corrupt data like this, and you see all this noise, but then you see some good data over here and you see some bad data there, that's more than likely one module causing that problem. It's still going to communicate, but it's going to kick whatever controller is causing that problem off the network. This one is weak controller packets. So in this case, internal shorts to ground. It's not powerful enough. And remember how I said if it doesn't reach a certain threshold, it's not going to be considered valid data. So if it doesn't go strong enough and it doesn't get up to our thresholds, then we're not going to be communicating. So once again, you could see bad data along with good data. Good data is the modules are good. Bad data, the module's bad. So a couple different scenarios we could have. So if the voltage on the high side is short to power, it'd be up above that 3.75 volts. If it's normal, it would be at the 3.75. And then if it's short to ground, it'd be down here on the bottom at 0. Same thing with the low side, short to ground, normal, short to power. Both could be short to ground, both can be normal, both could be short to power. One could be shorted to ground, one could be shorted to power. And it could work in any of the combinations of those. They can both be normal, of course. And then in this case, this is showing it not mirrored. So we got some bouncing down to ground right here. So that's internal shorts to power or ground. So if the internal shorts to power would be down this side. Internal shorts to ground would be down here. Internal shorts to power would show up there. And then this one's all sorts of messed up. Up, down, and all around. Not mirrored at all, once again. So that one's pretty messed up. If one side gets short to ground, a dead short to ground where nothing's going through, it'll still communicate, but at a lower frequency. Same thing with the low side, same deal. But if both of them are short, probably a break in the line. Probably got cut somewhere. All communication between controllers past that are going to be lost. Most likely a result of physical damage, like it says. So now we have a little case study to talk about bus problems. And this one's a little unique, and I think it's a pretty good story about that. So this is a 2015 Grand Cherokee U0403 code. So that's a communication code with the transfer case. So it says implausible data received from transfer case. And usually this doesn't throw in the engine, this will throw in the ABS or the transmission usually. So in this case, we'll go into Intelligent Diagnostics and diagnose it. We'll see top repairs. There's no TSBs on this, by the way, but it's implausible data received from transfer case. 20-something times replace transfer case control module, shift motor, engine mounts, stuff related to it. And that might be your first guess if you weren't testing or you didn't go through all the information. However, if we come down to the bottom here and we go to our real world based troubleshooter information and go in there, and you see there's a time saver right there. Maybe caused by a faulty ground connection, a damaged wiring harness, or water entering the transfer case module. Sounds all pretty legit to me. But it says, before condemning the vehicle's transfer case module, it's advised to check the ground strap for the anti-lock brake module, because they share it. It has been reported in the field that a population of Grand Cherokees left the factory with the ground strap not fully tightened. There have been several cases where tightening this ground connection resolves the problem. And that's a pretty easy thing to check. We're going to take a look at where it's located here in a minute, but it's pretty easy to get to, and you can tighten it up. And if it was loose, clear it and see if it comes back. Additionally, it's advised to check the transfer case wiring harness for any damage and check the transfer case module for any signs of water ingress. There have been several cases of this DTC being set by water getting in the module. Otherwise, follow the OEM's information for diagnosing this code. So, if I have this code, I can check the ground pretty quick. I can check for whether or not water got into it. If both of those are okay, then I move on and just use the OEM diagnostic trouble for it, right? Let's take a look at some more information. We'll go into the wiring diagram. So in shop key, we see it's got U0403 right there. And then we go to our wiring diagrams. And then here's the drivetrain control module, which would be the transfer case control module. And we see this ground right here, G901A. I see how it's highlighted. We could click on that. It opens up a search box and we can look for the location. And then it actually gives us a location right there, straight from the manufacturer. So it's up on the fender well there. Kind of close to the firewall, but it's right there. Easy enough to access. It's kind of right on the side. So somebody forgot to tighten a bunch of them, leaving the factory, and causes communication issues at some point when it gets loose enough. And then if we wanted to pull up the wiring diagram, the ground wiring diagram, and we can see there's that G901A right there, and all these modules share it. So drivetrain control module is one of them. ABS module is the other one. And then all this other stuff. So I imagine you might have some other problems. Maybe your lights are dim. Could be, right? So they all kind of share this one ground. So if we have a problem and it's loose, then we tighten it up. If it fixes the problem, perfect. All right, let's go live. Take a look at a couple examples on the tool of what we would see. First one I want to go through is, actually, before I do that, I want to go through and show you, if you have a Snap-on scan tool with a scope, you will have guided component tests available. Inside guided component tests, you can learn much more about CAN bus if you want to, or other networks. Up here we have classes, first thing, when we go to ID our car. And then if we go to how to, come down here a little bit, and it is a 20-minute CAN bus class right there. Got things like basics and fundamentals, bus arbitration, CAN voltages, error handling, signal quality, waveforms. Got a bunch of known good and known not good waveforms. Here's what it looks like if it's short to ground on the low side. Depending on where it is, it could look like this. So we give you a lot of really good information. This one right here is the two wires shorted together because they're putting the exact same signal out. They're not mirroring each other. So a lot of good examples there. Built right into the tool. And then also, if you wanted a quick preset, and you didn't need to necessarily go into a vehicle, you can go to power user test, dual channel test, and there's the CAN bus test right there. Yellow to CAN high, green to CAN low, hit view meter. It's going to set up the voltage. I got to turn on my simulator. There we go. It's going to set up the voltage, set up the time for you, put them where they need to be. It even gives you a known good pattern right here. And then it's going to say CAN high should pulse upward from about 2.5 to 4 volts and low pulse downward approximately 2.5 to 1 volt. And it should be about 2.5 volts right there. So we're pretty darn close. Looks pretty good. That's what it should look like. All right. So let's take a look at a couple of vehicles. So we're going to do this Ford pickup first. F-150. 2008 F-150. With a 5.4 3-valve motor in it. Good old truck. Everybody loves those, right? 2 million repairs on record for it. So finally, I'm just going to pull up the wiring diagram and take a look. And if you have Shopkey or Mitchell, there will be computer data lines listed in there. You can go into your computer data lines. In this case, this is one whole page. That's it. You can see the DLC connectors over here. You can see all the different modules here in purple. And we can see we have CAN, high and low. CAN again. UBP is what they use for programming, flashing. And then we have an ISO line over here too on a couple of these. So it seems like, interestingly enough, the power wire, this ISO wire, and so those two are light blue with white. So it's either power or it's communication line. So interesting. And you notice we also have these junctions here. They have joints. So these could fail feasibly as well. So if I get signal from here all the way over to here, but then I don't have signal here, but I do have signal here, then I'll know it's probably this one, right? So being able to interpret the wiring diagram to see where everything is can be invaluable. That's one example. Ford does it kind of an interesting way. Let's load this Subaru. Forester. Subaru does things in a unique way. They always have. Whether that's good or not, I guess it kind of depends on the situation. I'll go to my computer data lines again. Once again, this is a single page. And we can see any of the red, blue, or pink and blue are all CAN. So internally, it communicates with CAN. If I go to the diagnostic connector, you see it could also communicate at the diagnostic connector via CAN. But the factory tool on this vehicle still uses K-line. So right there, pin 7, violet. And then you'll notice that K-line goes into a junction connector, a junction block right there. So that, for one thing, this gives us a good access point because that'll send it to the body control module, sends it to the VDC, which is the vehicle dynamics control, TCM, ECM. All the main modules on the vehicle are going to be can be accessible through that joint connector if you needed to. Gives us a good test point. Also unique about this, though, is this particular joint connector is above the fuse box behind the dash. And these joint connectors, the actual connectors themselves, are about the size of a mini fuse. So you feasibly could have a customer go rooting around under there. Maybe they thought they had a problem with a fuse or something, and they see this and, oh, that looks like a fuse, and pull it out. And if you don't put it back in the right place, you lose communication with something. So that is another thing that you might have to worry about. Probably not very common, but you never know. Another joint connector over here for the internal CAN. And that goes from the body integration unit. So that's the body control module. And on these vehicles, that is the gateway module. So all the networks come in here and it translates from there. Then we have another CAN joint connector there. Also on the left side of the dash. And then that goes out to the meter, AC control panel, etc. So kind of unique there. All right, and then the last one I'll do is a BMW 328i. Oh, I am signed in too many times, so I'll just sign myself out. There we go. All right, 3-liter, 1052. Call it a convertible, I guess. Automatic. This vehicle. All right, pull up the wiring diagram there. Computer data lines, and this is on 2 lines. So we come down here. I'm going to go to the second one, sedan here. So computer data lines in this. You see we have multiple buses. So we got LIN there. We got power supply. We got KCAN. 2. Let's see, other data lines that it talks about. Oh, I got it on the picture itself. Bus diag, data lines, flex bus, Flexray bus right there, right? A lot of Flexray bus. PT CAN, flex bus again, bus signal, KCAN, KLIN, EC line, right? So we can see all of that. And then if I go across the way, that's going to bring us to the, where is it? There it is, diagnostic connector right there, 16-pin. This one actually has a terminating resistor in there between 6 and 14 for the CAN bus. Interesting. You don't usually see that called out on many vehicles. This one also, if you notice, it has a couple splice connectors there, but it doesn't have any of those termination blocks that we looked at earlier. So this one's fairly straightforward. You find out where your module is and where it is connected in the network. Seems like everything goes through this front electronic module here. So I guess that's your gateway module on this car. And you can test from there easily enough. If you knew what pin was what, you can go in, back probe it there, test it there. So if you're going to test these networks, you really need to get familiar with reading wiring diagrams, because that'll be your helper big time when it comes trying to diagnose, instead of just, oh yeah, it's not communicating, but I don't know where it is in line of the network. So if it takes half the bus down, I need to know where to start. So I need to be able to check those wiring diagrams. All right, that is my time. Let's talk about what we're going to talk about next week. So next week we will be continuing on with our OEM-specific ADAS training series, and next week it'll be Chrysler, Dodge, Jeep, Ram. So Stellantis Group, or whatever you want to call them now. So we'll be talking about what makes their ADAS unique, and some other, what makes them a little different from other manufacturers and how they do things, and what makes them the same as how other manufacturers do things. So we'll just do a little deep dive on each of the vehicles and show you some examples. So same time as always, 6 and 9 Eastern. 6 to 9 Eastern on in the United States anyways. 3 p.m., 6 p.m. Pacific. So session 1 goes to Zoom. If you want to sign up on Zoom, it's snapon.com/OT. So both sessions go to Zoom actually. And then the 6 p.m. Eastern class goes live to YouTube. And then the 9 p.m. class, like I'm doing right now, goes live to, or went live to, the Facebook page. Right. So our Facebook page is now called Snap-on Diagnostic Product and Training. It's got a big red Snap-on S inside, or white Snap-on S inside of Scan Tools logo. So if you want to follow us over there, that's fine. And if you want to subscribe on YouTube, that would be wonderful as well. We have the QR code right there. Just scan it, and it will bring you right to the page and subscribe you automatically. If you want to see any of the other classes in this series, anywhere from Intro to ADAS to OEM-specific ADAS on VW and Audi that I did last week, and everything in between. This is episode 116 right now. So once again, visit the YouTube channel to view all that information. And then, do we have your email address? If we don't have your email address, you may be missing out on some really good diagnostic related stuff, like technical focus articles, SureTrack blogs, quick tips, new product releases. They send out my schedule, I think, monthly. So you'll get only just a couple emails a month. It's not like we're going to spam you 5 times a day like some companies do. And this is an example right here of an article that we published on helping to diagnose the stretch timing chain. Right, good information. So if you want, click on that or scan that QR code. It'll bring you to a form you can fill out, put in your particulars, and then you can start receiving those emails. All right, time for questions. If you do have a question and you're on Zoom, just find that Q&A button, type it in. Otherwise, on Facebook, just use the commenting function, and we'll answer your questions, if any. Also want to mention my buddy Keith, who also does free diagnostics training, and he does diagnostics training for scan tools. So he does Wednesdays does Zeus and Zeus Plus, Thursdays Triton and Apollo tools. He goes through everything from soup to nut, start to finish. Let's get your Wi-Fi set up. Let's talk about Snap-on Cloud. Let's talk about navigating through the scan tool itself and what the buttons do. That's about an hour, and then he takes a 5-minute break in between, and then he goes through all the scope and meter functions on the back half of the class. So very informative, very well versed in Snap-on diagnostics because he's been with us since the Sun days. So very knowledgeable man on the subject. So definitely give it a shot if you want to learn more about your tool. All right, let's see. So I have questions. Here's a good one from Antonio. So he said 2019 Jeep Wrangler, communication issues with ABS module, typical issue, star connector. So those multi-joint connectors I showed you on the Subaru there also exist on many other manufacturers. So ends up being the star connector. And he said scope help watching the glitch when driven. It's not always the module. It's not. You're right. Not always the module. Sometimes it's a bad ground, like we saw in the case study. Sometimes it's the star connector. Something goes wrong in there. Excellent information. Thank you very much for that. Then on Facebook, Mike says, very informative. Thank you, Jason and Snap-on. You're very welcome. Thank you for attending. I appreciate it. And I did see Leighton chimed in earlier, too. So if you're still watching, hello, Mr. Leighton. Good to see you. Long time no see. So with that, I'd like to say thank you. Thank you very much for spending a little bit of time with me. Hopefully you learned a couple more little tips and tricks when it comes to diagnosing those pesky network problems. Hopefully you'll join me next week for ADOS on CDJR. With that, enjoy the rest of your week. Enjoy your weekend. Have a nice night and take care.